The overall goal of this procedure is to determine how closely a computer model of a handshake matches the human handshake. This is accomplished by first presenting the subjects with pairs of handshakes, either human, computer-generated, or a combination of the two, using a telerobotic interface. The second step of the procedure is to ask each subject to choose within each pair which of the two handshakes is more human-like. The final step of the procedure is to calculate from the subject's answers the human likeness grade for the handshake model, the Model Human Likeness Grade, or MHLG. Ultimately, results can be obtained that show a significant distinction between different models' MHLGs using the Turing-Like Handshake test.
The Turing test is actually limited to verbal intelligence, whereas scientists and engineers observed a large gap between artificial and natural intelligence in the motor control aspect of motor behavior. Many scientists thought about this motor version of the Turing test, but only recently have back-drivable robotic devices become abundant in research laboratories, facilitating the implementation of a simple, reproducible protocol for a Turing-like handshake test.
This method can help answer key questions in the human-robot interaction field, such as what are the key features of human arm movements which provide natural human touch experience.
The implications of this technique extend to our diagnosis of motor impairments, such as cerebral palsy. The next step is to build a robotic diagnostic device that can distinguish a healthy human handshake from an impaired one.
Visual demonstration of this method is critical, as the handshake movement through the telerobotic system is not natural, and it takes time and practice to learn how to handle and interact with the robot.
Following the original concept of the classical Turing test, the handshake experiments consist of three entities: a human, a computer, and an interrogator. The interrogator and the human are seated in the same room, but are separated by a screen, and so the interrogator cannot see which one, the computer or human, is generating the handshake. The handshakes are not direct handshakes, but are accomplished through a mechanical telerobotic interface made up of two phantom desktop robots in the case of a human handshake, and one phantom robot and software in the case of a computer handshake. When the word handshake appears on the computer screen, the interrogator and the human immediately make handshaking movements by moving the stylus of the telerobotic interface in the vertical direction. The interrogator's job is to compare two handshakes and select which one is more human-like by pressing the Home or F1 key to choose the first handshake, or by pressing End or F2 to choose the second handshake. The three experimental protocols demonstrated in this video differ from each other by the composition of the handshakes that are compared. The first protocol is the pure Turing Test protocol, where the choice is between a human handshake and a computer-generated handshake. The second protocol includes handshakes that are varying compositions of human-generated and computer-generated forces. The third protocol includes handshakes that are varying combinations of a human-generated handshake and noise, or purely computer-generated forces. During the experiment, a random file is created automatically. At the prompt, enter a name for the random file. If the file already exists, the system uses the existing file. Otherwise, the system automatically generates a new random file with a specified name. The random file defines the order in which the different handshakes occur. The pure protocol starts with 12 practice trials of 2 handshakes each, in which the human and the interrogator shake hands 24 times through the telerobotic system. The interrogator knows at this stage that he shakes hands with a human. The purpose of these practice trials is to familiarize the participants with the telerobotic interface. Following the practice round, a block of 4 trials is done. In each trial, a human handshake is compared to one of 4 computer model handshakes in a random order, as shown in this example. For example, in trial 1 of block 1, the interrogator shakes hands twice. The first handshake is generated by the human, and the second handshake is generated by the computer using the forces dictated by Model 3. The interrogator then selects between handshake number 1 and handshake number 2 to decide which handshake is more human-like. For example, if the interrogator selects handshake number 1 as more human-like, the interrogator has chosen the human handshake. However, the interrogator is not told whether he or she has correctly identified the human handshake. In the next trial, the interrogator's first handshake is with the computer-generated Model 2, and the second handshake is with the human. The interrogator again selects the most human-like handshake. 2 more trials are done in a similar manner to test the remaining 2 models, Model 1 and Model 4, against the human handshake. This completes 1 block of trials. The experiment consists of 11 blocks of 4 trials each, with the 4 model handshakes presented in random order in each block. The initial block is a practice block, and the analysis is done on the remaining 10 blocks. After completing the 10 blocks of the experiment, each of the 4 handshake models has been tested 10 times against a human handshake. After completion of the 11 experimental blocks, a model human likeness grade is calculated for each of the 4 tested models. The analysis is done by calculating the proportion of handshakes in which the subject says the model handshake is more human-like than the human handshake. For example, if the interrogator chooses the Model 1 handshake over the human handshake in 2 of 10 handshakes, the proportion of model to human would be 0.2. Multiply this proportion by 2 in order to obtain the model human likeness grade for each model. With a proportion of 0.2, the Model 1's model human likeness grade would be 0.4. If Model 3 was selected as more human-like in 4 out of the 10 trials, then its proportion would be 0.4 and its model human likeness grade would be 0.8. If a model is indistinguishable from a human, its calculated proportion would be 0.5 and the model human likeness grade would be a 1. If a model is clearly non-human-like, its model human likeness grade would be 0. The MHLG is capped at 1. In this protocol, the generated handshakes are part human, part model, where the specific combination varies across trials on a scale from a pure computer-generated handshake to a pure human handshake. Therefore, this set of experiments is referred to as the weighted human model test. The protocol begins with a practice block to help the interrogator learn to recognize a purely human handshake and become familiar with the apparatus. Therefore, the practice block has 30 trials that compare a purely human handshake to a computer-generated handshake. At the end of each trial, the interrogator chooses which of the 2 handshakes was most human-like. If the interrogator correctly identifies the human handshake, the screen displays correct. If the interrogator doesn't choose the correct handshake, a wrong message appears and the interrogator has the opportunity to repeat the last practice trial. After the practice block, the interrogator begins a series of trials to evaluate 2 handshakes. The 2 handshakes are a stimulus handshake and a reference handshake, each of which is a combination of human and model forces. In the reference handshake, the handshake felt by the interrogator is an even mixture of the forces generated by the human and a computer-generated model. In other words, while the human participant makes handshaking motion, that handshake only makes up 50% of the force perceived by the interrogator, with the remaining 50% of the force coming from a model. In the stimulus handshake, the handshake felt by the interrogator is a varying mixture of the forces generated by the human and by a computer-generated model. In some of the stimulus handshakes, the fraction contributed by the human is more than half, and thus more than in the reference handshake. In other stimulus handshakes, the fraction contributed by the human is less than half, and thus less than in the reference handshake. At the end of each trial, the interrogator is requested to choose the handshake that felt more human-like. This experiment compares 3 models, 2 test models and 1 base model. As in the pure protocol, this protocol begins with 1 unanalyzed block, followed by 10 experimental blocks. Each experimental block consists of 24 trials comprising each of the 8 linear combinations of model and human for each of the 3 model combinations. Upon completion of the 10 experimental blocks, a logistic psychometric function is fit to the answers of the interrogator, as described in the accompanying article. The resulting curve displays the probability of the interrogator to answer that a stimulus handshake is more human-like than the reference handshake, as a function of alpha stimulus minus alpha reference. The point of subjective equality, or PSE, is extracted from the 0.5 threshold level of the psychometric curve. indicating the difference between the alpha stimulus and alpha reference, for which the handshakes are perceived to be equally human-like. The model human likeness grade for the weighted human model protocol is calculated by subtracting the PSE from 0.5. The models that are perceived as the least or the most human-like possible yield model human likeness grade values of 0 or 1 respectively. The final protocol compares a model handshake to a part human, part random noise handshake. In this protocol, the stimulus handshake is a computer-generated handshake based on a model. The other handshake, the reference handshake, is a force generated from various combinations of the human handshake and white noise, with maximum absolute force of 2n, filtered using the low-pass Butterworth filter of order 5 at a maximum frequency of 2 over pi. At the end of each trial, the interrogator is requested to choose the handshake that felt more human-like. The protocol has a similar design to the previous weighted human model test. After a practice round and an unanalyzed block, a series of 10 experimental blocks is run as follows. The PSE is extracted from the psychometric curve as before and defines the model human likeness grade for the added noise protocol. This figure shows results from the pure protocol and compares human handshakes to two different model handshakes. The 2 points show the calculated model human likeness grade values for two viscoelastic models, named KB1 and KB2. The results demonstrate that the model KB2 is perceived as more human-like than model KB1. This figure shows the results from the weighted model human protocol, which compared a varying ratio of human model handshakes to a fixed 50-50 ratio of human model handshakes. The black markers represent the model human likeness grades for the test models, and the grey markers represent those of the base model. The error bars represent the psychometric curve's confidence intervals. This figure shows the results from the added noise protocol, which compares a model handshake to a handshake with a varying ratio of human to noise components. The black markers represent the model human likeness grades for the models, and the grey markers represent those of the noise. The error bars represent the psychometric curve's confidence intervals. These results demonstrate that the viscoelastic model KB2 is perceived as more human-like than viscoelastic model KB1, using all three evaluation methods.
While attempting this procedure, it is important to remember to interact with the robotic device properly and try to make the interaction as smooth as possible.
Following this procedure, other methods, such as testing recognition of human handshakes in pervasive developmental disorders, can be performed in order to answer additional questions, like how do pervasive developmental disorders affect the ability to distinguish human from non-human gestures?
Now, after its development, this technique can pave the way to use handshake as a recognition tool. We hypothesize that the purpose of handshaking is to learn something about the other person. Therefore, the methodology we propose for developing a human-like handshake can also facilitate the development of handshake classification system, which can extract information about the other person from his or her handshake.
After watching this video, you should have a good understanding of how to perform the one-dimensional Turing-Like Handshake test, and how we're going to evaluate handshake models submitted to the first International Turing-Like Handshake Test Tournament.